In this video, we're going to talk about a special kind of graph which is known as a tree. A tree is a graph that has the following properties. One, it's connected. The second property is that it's undirected. And the third property is that it has no circuits. And so far, we've only really talked about this right here, that we have an undirected graph, which as a reminder is a graph that has, maybe one or more different nodes and one or more different edges in it, and none of the edges have a direction associated with them. And basically that means that, the edge works in both directions. So in this example here, maybe A is connected to B, and also B is connected to A. So it works in both directions, right? So every single tree that we have is going to be undirected. But we even talked about the idea of connected and having no circuits. So let's talk about those in a bit more detail. To understand the idea of a connected graph, we have to understand the idea of what we call a path. A path is basically a way of being able to move between different nodes in a graph. So in this example here, it's possible for me to start at A, move over an edge, and end up at B. This would be an example of a path. It's basically a representation of a way that we can move from one node to another using connections between them. So in this example, there's a path from A to B because there's an edge that connects A and B together. Similarly, there's actually another path that connects A to B. I could go from A to C, and then I could go from C to B. So this is an example of another path. So there's two paths that could take us to B in this graph. One that goes from A to B, and then there's one that goes from A to C to B. So a path just represents a way of being able to move from a node to another using the edges between the different nodes. When I say that a graph is connected, what that means is that there's a path between all of the different nodes that exist inside of our graph. So when we take a look at this graph here, this graph is connected because I can start at any node in my graph, and I can create a path to any other node in my graph. If I were to add another node in the middle D that had no edges, this graph would not be connected because there's no way for me to start at D and get to every other node. There's also no way for me to start at, any other node and get to D. So that would not be connected. However, if D wasn't there, then the graph would be connected. So that's the idea of the nodes being connected. So we got that. What about the idea of having no circuits? What a circuit is it's a path that starts at one node in our graph, it goes to a different node, and then it ends up back where it started without traversing the same edges. So for example, there's a clear circuit inside of this graph that I've drawn here. We can go from A to C, from C to B, and then we can go from B back to A. Do you see how I didn't travel any of the same edges, right? I went from A to C, so that's one edge, C to B, which is another edge, and then B to A. So we traveled three distinctive edges, and we ended up back where we started. This is an example of a circuit, right? So that's a circuit. Our goal with a tree is to have no circuits in it. So this graph right here that I've shown is not a tree because it has a circuit inside of it. It was close, right? It was connected, it was undirected, but it has circuits in it, therefore it's not a tree. So then what would be an example of a tree? Well, let me draw one out for you here. I'll remove this piece here, and then I'll draw out an example of a tree for you. So an example of a tree would be a graph that looks something like this. And I'm really drawing like the most typical tree ever. There's a lot of different ways that we can draw trees, but this would be a very typical example of one. Why is this a tree? Well, first off, it's undirected, right? None of the edges have directions on them, so that's a good starting point. The second property that we are connected is pretty clearly the case, right? If I start at any node, I can get to any other node in my tree. There's no node that is impossible to reach from any starting point. I can start anywhere in my tree and I can get anywhere else. So my tree is pretty clearly connected. Now, what about the lack of circuits? Well, the lack of circuits part is an interesting one, right? When we take a look at this, if I start at my top node here, which I'll call my root node, since it's the common terminology that we would use for this node here at the top. If I were to move over to the left-hand side of my tree, right, you can see that there's no way now to get to the right-hand side without traveling the same edge. So no matter where I go here, I can't go back where I started because I'd end up traveling over the same edge again. That's because there's no like connection that looks like this, right, to connect these two together to bring us back where we started, right? Similarly, if I go to the right-hand side, there's no way to connect myself back up to the original starting point, nor to the other side of the tree. Because of that, we could see that there's no real way to create a circuit between any of these different edges. No matter where I start, I can't ever really get back where I started because if I end up somewhere else, I can't ever connect back to where I am currently, right? So this one looks to be a valid tree, right? So this would be a great example of a tree as a graph. And for that matter, actually, it's a great example of a special kind of tree, which is the main one we're going to talk about, which is a binary tree. And we might as well talk a bit about this before we proceed on to actual implementations of this. The idea of a binary tree is that it has a root node, and this root node is sort of like the starting point of the tree. And every single node that's below it is going to be a part of the tree, right? And basically each tree can have at most two nodes that are connected below it, which we will call the children of the node. So you'll see here that the root, in this example here, has two nodes connected to it. These are the children of the root. The root here would be called the parent, in this case here. And then do you see that this node here, it has two children connected to it. And this node here has two children connected to it, right? No node has more than two children, so we call this a binary tree. As the name implies, two different children, right? Now it's important to note with this kind of tree that we don't necessarily need two children every time, right? We could have a tree that looks something like this. This tree is also a binary tree because no node has more than two children. A node can have one child, it can have 0 children, it can have 2 children, but it can't have any more, right? So you see here that this node here, it's only got one child to it, which is okay. That still satisfies our property. This one here has 2 children associated with it, and our root node also has 2 children. So this is a binary tree. So this gives you a bit of intuition around what we're really talking about when we're talking about trees, and more specifically, binary trees. In the next video, I'm going to introduce to you the idea of a binary search tree, which is a very important data structure in computer science, which allows us to search through sorted values and store data in a sorted order to be able to retrieve data in a fairly quick time complexity. So we'll take a look at that in the next video. Thanks so much for watching. I'll see you in the next one.